All right. Well, thank you so much for joining today with KUKA Robotics as we talk about the LBR Easy. We are going to be going through a 1-hour presentation, and we'll make sure to have some room for questions at the end. So if you have any questions to get started, feel free to put them in the poll, and we'll go through it towards the end. So my name is Mitch Katosin. I'm an account manager at KUKA Robotics, and I am joined here with co-host Austin Helm, who's an application engineer. Both of us have been working at KUKA for a few years, so we're excited for a new product to be kind of do a dive into this new product, the LBR Easy, and share some insight into how we could unleash the power of the new KUKA lightweight robot through this webinar. So just to get started with an overview and agenda, we're going to go through a few different key parts of the LBR Easy. That includes the portfolio and configurations of the system, some of the main features and capabilities, operational modes, and then safety tooling and the external API control, which really allows you to utilize and leverage this arm for rapid prototyping and other collaborative applications. So the system itself, if you just go back to that slide for a second, I apologize. The system itself is, within a portfolio of arms that we provide at KUKA. As a global leader in the robotics market, KUKA has a lot of different options for different application and use cases. The LBR Easy is one of those systems that we provide to the marketplace. And this system has kind of 3 key features that we're going to talk briefly about through the presentation, but I wanted to give a quick overview so you kind of have a large view of the different options. So that first one is the KRC5 microcontroller. That is the controller that the LBR Easy runs on. It's a very small controller, and we'll talk a little bit about the technical data regarding that controller. And then as far as programming and just viewing the system, we have a SmartPad Pro, and this runs our software, the KUKA, that runs the LBR Easy. And then we also have an external control interface, which you can connect to different external libraries that make it a real-time controlled system. When you talk about collaborative applications and the collaborative spectrum, there's kind of 2 key markets. And today we're going to talk about this bottom hand market, and just to help kind of guide our discussion today and kind of highlight this system, I wanted to break that apart from maybe what you could consider as like a high level or high complexity or payload control system, such as the LBR EWA or MED, which are sister robot or cousin robots of the LBR Easy. Some of the differences here on the higher level would be higher sensitivity applications or an advanced feature sets that comes with the robot, or complex system control and architecture, where the lower hand box, which is the LBR Easy, is a much lower cost system. It's great for rapid prototyping or simple motion capabilities and feature sets that come kind of generic out of the box, where you have a little bit more work to do. But again, you get the benefit of a lower cost option, and it's very competitive with the market of things like other collaborative robots that have been utilized for lots of different applications, like machine tending or even some imaging applications, things like that. The market itself has been increasing for collaborative robots. So the Easy is, coming in at a good time when you think about where the market is. Over the last 3-4 years, we've seen a growth in the collaborative market, and particularly, I just wanted to show a quick slide on some of the different markets that collaborative robotics have been utilized for. So automotive, food and beverage, metal machine, electronics, pharma. These are all kind of pieces of the pie, as well as the upcoming kind of medical market as well. We we're gonna, I think, jump into the portfolio and configuration of the easy and kind of zoom in now on the easy itself. So the LBR easy portfolio comes in 5 variants. We have the easy 3, which is kind of its own unique form factor, and then we have the easy 6, 8, 11, and 15. Now, these are all the payloads. They're all 6 axis robots. The form factor of the 6 and 11 are the same. The difference is the motor boxes and the gearboxes that go into those arms. That's what determines if it's a 6 kilogram payload or 11 kilogram payload, as well as the 8 and the 15. They are the same form factor. So you really have 3 different body types, but you have 5 different options when it comes to the LBR easy. These are IP rated for 54, and they basically, the LBR easy 3 is IP rated for 30. So it is quite a bit different if you're in applications working with any type of particles or water resistant type of environments, then you do want to stick with an IP54 system instead of IP30. But other than that, they're very comparable when it comes to things like the safety performance level or how they can be mounted, and the reaches are slightly different. So between the 6 and 11 is a 1300 millimeter reach, and the 930 millimeter reach is for the 8 and the 15. So depending on the application, you're looking at a maximum reach of 1300 millimeters from base to flange. Sorry about that. The technical data regarding the arm itself, really, I just wanted to zoom in on 2 things here. Under the right-hand side, the mounting base of the arm is a generic mounting standard frame. So it would kind of be conformed to different types of ISO standards, as well as the flange. That is another, standardized connection to make it easy when you're connecting to different tables or grippers or tooling that you might want to add onto the arm. The other thing that's important to notice is the temperature range for storage. So it goes from -25 Celsius to 70 degrees Celsius. So that really meets a lot of the standards when you're talking about shipping the system, if you were to create kind of a product out of it with, a specific application in mind. And then additionally, the access speeds there. You can see that it is pretty fast for a collaborative robot. And that's going to take us kind of into the feature and market comparisons. So there's just like some basic research when you're comparing the system to other systems in the market. The repeatability of all of the arms except for the 3 kilogram payload arm are a repeatability of 0.03 millimeters. All systems have force torque sensors on each axis. And one thing that I really think is valuable about this LBR Easy is that it's built on the KUKA Agilis platform, which is an industrial platform that we've had in our portfolio at KUKA for quite a while. So it ensures that it's reliable and that it has extremely high stiffness. It's one of the most high stiff robots I've ever had ever interacted with. Additionally, with the external API control, we can achieve the 1 millisecond real-time communication. That's very common in different types of real-time applications. We have hand guiding functionality that is very smooth with this arm. When you compare to something like a UR arm, you'll see a big difference in how easy it is to move the system around with your hand, how the system drives itself based on the force feedback of your hand. And then of course, we have priced the system to be cost competitive to the market. Now, we did kind of average out a few competitors and picked kind of like the top 3 competitors in the market. And here are just some comparisons as you think about collaborative applications. So from an access speed, this is something that I mentioned already, but to see it compared to the average of 3 different competitor systems, you can see that it is much higher when it comes to motion capability. So this is degrees per second, and then per joint, starting with joint 1, ending in joint 6. And then the pose repeatability, again, is higher. The reach and payload is a bit longer with a slightly larger payload at that reach. And then the controller, which is a much more lightweight option compared to the market, as well as much smaller option. So if you look at that 392 millimeters by 300 by 137 millimeters, that is the volume of our controller versus the kind of average of the top 3 competitors, which are about 444 millimeters by 381 millimeters by 269 millimeters. So you can see a much smaller controller size. And then lastly, the mastering. On any type of robot, you do have to do mastering to make sure the robot is where it is expected to be. And that kind of is defining the 0 position on each joint. With LBR Easy, you do not need any type of external device to do this. It is done through the smart pad. The robot moves and ensures that it knows where the notch is for 0 position, and in all of the other market comparisons, you would need a service engineer to handle the situation. So those are just some quick features of the LBR Easy and some of the benefits of the arm itself and even the controller. And now we're going to jump into kind of more about the details of the system itself. And we'll start just with how do you use it? What are the operational modes that you have available to you with LBR Easy? So the first operational mode is smart programming. So basically, the system is set up to do a graphical type programming. This allows you to leverage some pre-canned features such as like looping or moving to a specific point or creating inputs or outputs or force control. And you can drag and drop these into your graphical program to create something like this, which would be an program. And you would have something like an if statement to determine when it should start, and then moving to a position, initiating a certain amount of loops, and then moving home. So this is like the first initial way that the LBR Easy is designed to work. It makes it easy for doing a very small application and doing something like a pick and place program. The second way is using the ExternalAPI.Control Interface. This uses kind of like a library that you would download from KUKA, which is our online web-based platform that allows you to grab different types of developed software and utilize it for the system. So you would download this external API, and it would allow you to take the robot over with a single point of control safely, which is kind of like a beautiful compromise. So you get that real-time capability, but you get it done with the safety that you've kind of implemented in the software suite. So here we're just showing where you can go on the smart pad to get the available toolbox, and you can see here that you actually can connect to KUKA and through your network, through Wi-Fi, and download the system. So as you go through improvements with the software, you'd be able to download those directly from our platform. The last option you have for operations is just the graphical visualization on the smart pad or on your PC, where you can get live updates. You can see safety zones and tool zones as well, which is really nice for just visualizing what's going on in your workspace. So the next section will be the actual hardware of the LBR Easy, and I'm going to turn it over to Austin. Thanks, Austin, for jumping in and walking us through some of the other features of the LBR system.
Thank you very much, Michka. So as Michka said, I'll be taking care of the rest of the presentation. My name is Austin, and as Michka mentioned at the beginning, I'm an application engineer for the medical business unit here at KUKA. And so I'm going to be taking care of some of the hardware, a little bit more of the software features concerning safety and tooling, and then I'm going to finish it off with the external API toolbox. So with the hardware, we can start with the commander. It's at the end of the flange, and there's a couple cool features with the LBR Easy commander. So one of which is the built-in safe enabling switch. So this allows you to have easy hand guiding straight out of the box. You don't need to set up a hand guiding device or foot pedal. You can just use the switch at the commander. There's also a toggleable button and thumb wheel for easy to program, and you could use it to like teach up your TCP points. It comes with a standard ISO flange and outlet for energy supply, which we'll get more into in a minute. And lastly, it does come with a LED ring for status indication, so you can tell easily if the robot's in an error state or a ready to go state. So just covering the buttons on the commander a little bit more in depth. One example that you could use those for are touching up points. So let's say you have a tool and you want to teach some TCP. I could use the dial to select which pose I want to teach, and then I could push in the dial button to teach up or touch up a point in space. So it's implemented into the software to make programming a little bit easier, and in a sense that you don't always have to touch the smart pad to do what you need to do. So regarding the integrated energy supply in the robot, there are two pass-through cables that go from the back of the robot all the way through the arm out to the flange commander. So the first cable set is a Gigabit Ethernet Cat5e cable. It's an 8-pin connector, and the second cable is a 6. It has 6 I/O and 2 wires for 24 volts. So that gives you 8 wires at the flange. So if you need like an EtherCAT protocol connection, you could use the Gigabit Ethernet cable. And if you just need standard I/O with power, you could use the secondary 8-pin connector. So connecting to these cables, KUKA does have a BiPAC connector. So the X74 is the Ethernet 1 gigabit connector, and the X76 is for your standard I/O with the 24 volt power supply. And then at the flange, the robot has a blank panel, so you don't technically have cables coming out of the panel when it comes out of the box, but the BiPAC A6 allows you to swap out that blank panel so you have easy to access cables coming out of the side of the flange. So it's just a nicer looking interface to pull your cables from inside the robot. So now we're going to jump into the software side for the safety and tooling. And this is going to be geared a little bit more towards if you're using the external control API. So the safety concept with the LBR Easy is set up to be fully customizable and configurable by the integrator. So since it is a collaborative robot, and KUKA understands that each collaborative application is going to be slightly different, we allow the customer to configure the different states that the application might need to monitor. So as you can see, there's a couple different concepts like safety rule set, safety rule, monitoring block, and reaction. And essentially the safety is set up in a way such that there's a safety rule that is monitoring up to 6 conditions. And if all of those conditions become violated, then a reaction occurs. So in the picture, you can see there's a enabling test mode, which is a safety rule. And it's monitoring 3 conditions: a test mode, a manual guidance inactive, and an enabling inactive. And if all 3 of those blocks are monitored and violated at the same time, then the enabling and test mode safety rule will output some reaction. And in this case, the reaction is a stop one on path. So you're able to customize a specific safety rule and monitor different conditions like maybe a safe output, if the robot is in a keep in or keep out zone, whether there's a collision detection, and then have the appropriate reaction for what you want the robot to do. Maybe that's just a generic safe output, or that could be stopping the robot. The other really cool thing about the iKUKA safety is that when you have changes and you do apply and approve them as the safety maintenance technician, it does generate a safety report and gives you all of the different rules, monitoring blocks, and reactions that you have configured, and puts them in a nice little PDF. So here's just a quick video of the iKUKA safety runtime environment. So if you are using the robot and you're trying to see what's violated, it is cool that you can see the states change. So here I'm pressing the hand guiding button and you can see the different monitoring blocks, or in this case, the circles, are changing based on the states that the robot is receiving. So with tooling, the actual concept for tooling changes a little bit between if you're using the generic SmartPad iKUKA programming environment, or if you're using the external API control toolbox, which is our real-time commanding. So in both cases, the tooling concept is the same, and that's if you mount a tool onto the robot flange and you don't configure the load data, any control loop with force or torque as an input will be negatively affected. So what that means is if I mount a tool on my flange and I don't tell the system that there's a tool on the flange and I try to hand guide the robot, because force is a factor in that control loop, the hand guiding will not be smooth. You'll be lifting the whole weight of the tool and the robot. So anytime you connect a tool to the end of the robot, you do need to let the robot know that there is a payload attached and provide the correct load data. This way, it prevents false positives and collision detection. Your hand guiding will be smooth. And if you're using impedance control, that will also function properly. Now, if you're not using the external API toolbox, but you are using the SmartPad drag and drop programming, then you could also have the other features, such as adding capabilities to your tool for I/O and adding TCPs onto your tool that you can use within your drag and drop programming. So now we're going to jump into the external API.Control toolbox. We're going to talk a little bit about the toolbox overview, the toolbox architecture, and some of the differences between this external API control toolbox and the normal drag and drop iKUKA programming. So what exactly is this external API.Control toolbox? It is a hard real-time communication interface for both monitoring and commanding robot states. And this provides a unique solution to our customers in the event that they want to do some more advanced trajectory planning or custom control loops. So out of the box, the robot comes with generic PTP, LIN, circ motions. But if you have a scene that may have some objects that are dynamically changing and you need to plan a path around them, then using this toolbox is very helpful in doing like collision avoidance. So with this toolbox, there are 3 different modes that you can use. First is joint control, then joint impedance control, where you can adjust the stiffness and dampening of each joint, and then torque control. So this allows you to control the torque and position of the robot. And the way that you interface through these 3 commanding modes are either through our ROS driver or our C++ SDK. So on the right-hand side, you can see we're using the ROS2 driver to do some collision avoidance, and you can see the path that the robot's going to take, and each of those little dots on that path is a point in space that the robot is moving to. So we're able to command specific trajectories around objects. So if you are familiar with any of the other offerings that KUKA has in terms of real-time toolboxes or option packages, this external API.Control toolbox with iKUKA is very similar to the Sunrise LBR Med FRI, and the KSS RSI. So again, it's a real-time interface. It has 4 millisecond cycle time, or like 1000 hertz transmission rate. It has the C++ SDK that you can implement, and or ROS2 driver if you want to leverage the ROS2 API. And again, the different supported functionalities. So how does the architecture of this toolbox actually work? I'm not going to go into a ton of depth, but at least give you the general overview of what that might look like. So on the right-hand side, we would have some external PC. And this external PC is responsible for our control layer for the robot. So it might do some planning, it might pull in a scene, plan a trajectory around some object. And once it's built this trajectory motion, it will supply all of those points to our client-side API. And this client-side API would either be that ROS2 driver and or the external control SDK, that C++ SDK. Now, from that client-side API, those pieces of data would be transferred for state management over TCP, over motion commands, it would be UDP. So all of that data is transferred over to the controller in real time. And once received by the controller, it's ported directly into our motion framework. And this way, anything that you plan on the external client, it's directly ported into our motion framework container. So we don't have any filters in between. It's literally whatever you command on the external client, you will see the exact same commanding on the controller side or robot side. So it gives us this real-time capability. So let's talk a little bit about the differences between programming through the KUKA environment versus the external API.Control environment. So on the left-hand side, we have an example of programming with the KUKA OS programming, the drag and drop. You can see if we have a program, we're able to pull in frames that we have taught. We can pull in tool control, so opening, closing the gripper, maybe some IO with the conveyor, your work pieces, picking them up, setting them down. But you lose the capability of connecting to an external PC. So if you need to stream data from an external PC, or you need some more advanced trajectory planning that's not available in the KUKA programming OS, then you would need to use that external API toolbox. So on the right-hand side, we do have the external API toolbox, but unfortunately, you do lose out on the frames, tool control, IO workpieces that have been integrated into KUKA OS. And this is due to that single point of control, because now the single point of control is on the client side. So that's what's controlling the robot. And this is due to the safety system. So the single point of control now is on the external PC. So you can see we have a client script. It's gonna maybe do some calculations for trajectory planning. It sends it to our ROS2 or external control C++ SDK. All of that data gets streamed to our toolbox on the controller, and then that gets sent over to the robot in real time. With the tool control, the IO, the GUI for starting and stopping a program, that is now up to the integrator to implement. So for example, and there's a ton of different ways you could do your tooling. This is just one example. The client script might have some tool control that goes to an IO, and then over EtherCAT might send the information to a backoff module and send it to the passive cables in the robot to control some tooling at the end of the flange. So what you see in orange is stuff that's capable through KUKA's specific interfaces. What you see in gray is specific to the customer and what they would have to implement. Now, what's really important to note is that in both scenarios, before information is sent to the robot, it does go through that safety layer. So if I try to command something in the real-time interface and the robot attempts to do it and it can't do it, the safety will trigger, in which you'll actually see an example in one of the videos later. Last but not least, the tool dynamics in both scenarios is abstracted. So it's there So if you, like I said before, if you implement the tooling, the load data, in both cases, whether you're using the normal programming environment or the external control toolbox, the load data will be accounted for. So you don't have to worry about accounting for tool data in your client script if you're using the external API toolbox. So now we're going to jump into some application development with this ExternalAPI.Control toolbox. So we're going to talk about the C++ external control SDK and rapid development with ROS2, and then provide some examples on how you can leverage these interfaces. So the first interface is the mandatory interface, and this is the C++ SDK. So it's mandatory from the sense that this is the framework for the toolbox to work on the client PC. So maybe you're interested in using the ROS2 driver, but you don't want to use this specific C++ SDK. That's okay, but this SDK is the basis for the ROS2 driver as well. So with this SDK, it provides you with the lowest level of real-time commanding and monitoring. It might not be the best use for generic applications, as you are having to create your trajectories from scratch, but for advanced applications, it's extremely useful because you do have the best and most control over the robot, because it is the lowest level of control that you can get. So for example, if you wanted to do some custom hand guiding with virtual walls and limits, it's up to the integrator to implement that. And there's no like API biases that KUKA would have added in to adjust the output. So it gives you the most level of control because it is the lowest level of control. Likewise with like teleoperation, you could use this API for teleoperation as well. In terms of rapid application development, ROS2 might be the more logical case because you're able to leverage the ROS2 API. You can leverage RViz, which is a robot visualization suite for simulation. And you could also leverage MoveIt2, which is an API for motion and trajectory planning. So as I mentioned in the last slide, with that C++ SDK, you would be responsible for both the motion planning and trajectory planning. But if you use a library like ROS2, you just give MoveIt a point in space and it will actually compute the trajectory for you. There is no need to compute the trajectory with ROS2. You just provide it a point in space and it will be able to move to it. So because of this, in all the libraries that are extended through ROS2, it makes general application development a lot easier, like pick and place, machine tending. There's a lot less overhead in the programming, unlike what you would see in the C++ SDK. On the contrary, because ROS2 is a little bit more of a higher level control compared to the C++ SDK, you might not have as many options with advanced applications, although you still have several advanced applications. So like collision avoidance would be a very common one with ROS2, as there's already a lot of collision avoidance libraries. But something like telemanipulation might be better with the C++ SDK, since there's less overhead than with something like ROS2. So we're just going to jump into a few examples here. So in this case, we have telemanipulation. And so I'm using the haptic feedback device from Happily Robotics to do some planar motion with the robot. And the C++ SDK is being commanded in joint space. So I'm basically getting the joints from the robot. I'm doing some forward kinematics, offsetting the robot by whatever I see on the telemanipulative device, and then I'm performing my IK and sending those joint data over to the robot in real time. So I could also get my torques from the robot and provide some force feedback into the telemanipulative device. So one application that this could actually be really useful for is maybe like an ultrasound, where you have a probe on the end of the robot and you're using the probe to touch the stomach, the nurse could be able to use the telemanipulated device and be able to feel the force feedback from the robot when the ultrasound probe is touching the stomach. Now, this specific example is using the ROS2 driver interface. And on the left-hand side, you can see RViz working. So there's the visualization, the simulation, and we have some planning scene that is running. And so the planning scene has a table. It also has the boundaries for where the torso is. And so we basically portray this torso as a box. So the box is bigger than what the torso is, so we can guarantee that the robot does not collide with the torso. In this case, we're using a collision avoidance library within ROS2 to be able to avoid robot collisions with the torso. And so this would take into account your tooling as well. So if you had some tooling attached to the robot and ROS2 knows about the tooling, it would actually generate a trajectory so that your tooling does not touch any of the collision objects within your planning scene. Now we'll have a more advanced application here with this collision avoidance, just another demonstration. So here I've only given it 2 points. So all of the trajectory planning that's happening right here is purely on the ROS2 side and not from my side. So I've given it 1 point on the right side of this foam pillar and 1 point on the left side of this foam pillar. So in this case, point 1 is right here. And the whole motion from moving from the right side to the left side is all generated by ROS2. So you can see how powerful ROS2 is in terms of rapid application development. If I know what my scene is, I can just provide a few points, use a collision avoidance library, and be able to rapidly develop some example application or proof of concept in application. And having a low-cost robot provides more capabilities in being able to do this. So another thing that's really nice with the ROS2 interface is that we do have a simulation environment. So we're able to mock the hardware from the driver. So if you don't have a robot and controller yet, or you're looking at ordering one and you want to see if the robot could be used in your specific application, our ROS2 drivers are a great choice because you can actually mock up a test scenario in your visualization suite and be able to test and program the robot without even having a physical robot. So here's one example of me doing some simulation with the robot. I'm mocking the robot hardware, and we're just doing a generic circle motion. So I'm going to show you a demonstration between what real life looks like and what the simulation life looks like. So here we have some simulation, but if we go to the next example, this is the real life example, and you can see I'm deviating the robot off path, and that's because in the simulation, I'm only in joint control, but in the real life scenario, I actually put the robot in joint impedance control. So it's cool to be able to see that you can test stuff in simulation, but you can also test the same things in real life and using like loops that have force as an input. So in this case, I'm pushing on the robot, I'm deviating off path, but I'm not pushing on the robot hard enough to trigger some collision detection. On the right-hand side, I'm using the external C++ SDK to do some collision avoidance. Sorry, not collision avoidance, but impedance control. So I have like a pretty high stiffness on all the joints and 0 dampening. So you can see the robot's just bouncing like a spring. And at the very end of the video, I actually pull the robot hard enough to where the velocity exceeds the limits right there. And you can see the status indicator goes red. And this is a great example of what I was mentioning in one of the previous slides, where the safety is always the highest level of control. So if I command something bad from the SDK or ROS2 and the safety catches it, it will stop the robot, maintaining that safe collaborative robot. So last but not least, let's just discuss how we can actually set up this external control toolbox and how do I actually get my hands on these drivers, the C++ external control SDK driver and the ROS2 driver. So if you're going to be working with an actual robot and controller, obviously you need an actual robot and controller. More specifically, you would also need the iKUKA OS 1.2 running on your KRC5 Micro, and additionally, you would need the Toolbox 1.3 for the external API.Control. As far as the controller configuration goes, make sure the Toolbox is installed. Configure the XF7 Kony port to a static IP address. This is really important because the Kony is the real-time port. Now you could use the KLI, but the KLI is not a real-time port. So it's best if you use the Kony port. Lastly, with that, make sure you try to have the XF7 or the Kony port directly connected to the external PC. You could have it go through a network switch, but the rule of thumb is less network traffic, better the real-time performance, and it does make a difference. Make sure you have the controller set to auto, and lastly, you need to release the single point of control, or the SPOC, so that way we know that the external PC is the device that is actually controlling the robot. As far as the drivers go and how to get the C++ SDK and the ROS2 drivers, you can download them from our GitHub called Crowshoe. It stands for KUKA ROS Hungary. And so the Crowshoe GitHub houses both the external control C++ SDK and the ROS2 interface. So as I mentioned before, the external control SDK is required, and it's kind of like the foundation API, and the ROS2 interface is built on top of it. So if you want to use the ROS2 interface, you'll ultimately install the external control SDK, a part of the ROS2 driver. Now, you have to use Linux, a Linux PC. You could use other installations of Linux like Red Hat or Debian. However, we recommend Ubuntu 22.04 as that's what all of our drivers and tests have been running on. And additionally, probably the most important part of all of this is the real-time kernel. This is very important because without the real-time kernel, the scheduler on the PC might not get the data to the robot in time, and you'll have broken up commanding. So the guys in KUKA Hungary have been gracious and provided a real-time patch setup and configuration guide on their GitHub page. So you can follow the instructions on how to build a real-time kernel and install it onto your PC. That way you have smooth commanding and your actual real-time commanding is not broken up. In terms of installing, you can follow the GitHub instructions for the SDK how-to README documentation, and for the ROS2 driver, the README documentation. So thank you all for attending the webinar. That is the end of the EasyCobot webinar. If you have any questions, you can feel free to reach out to our team, me specifically, Austin Helm, for the application engineering or technical questions. You could also reach out to either our Director of Medical Robotics, Corey Ryan, or our account manager for medical, Mitch Gatosin, and they'd be able to answer your questions on the robots concerning sales, or how do I get my hands on one of these robots. So I just want to thank you again for your time for this webinar. If you have any questions now, you can feel free to drop them in the chat.
Yep, so Austin, we do have one question currently open. Yeah. It was, how do I view the I/O that's on the robot on the iKUKA software, specifically ones that are coming out of the arm? The question goes on to say that I guess he has an arm, he can see the ones listed from the KRC or the KRC5 microcontroller easily, but he can't see the ones that would be connected to like the 76 or 96 I/O cables.
Okay, that's a good question. So I know that there's a tab. So where you would find your payload or your safety, there should be a tab for I/O, and you need to have the correct bus, I believe, picked. So there should be like a KCB KUKA controller bus, and there might be one for a different protocol. So you need to make sure that you are setting up the IO in the right tab. But feel free to reach out to me and I'll be able to provide some more information, since I don't have that exact information in front of me at the moment.
Perfect.
I think
Thanks.
it'd be helpful. Yeah.
Yeah, thanks, Austin. So if you ask that question, feel free to reach out to Austin or myself and we can navigate you through that. If there's any other questions, feel free to put them in the chat box, or there may be a poll button that you can click and put in a question. Give it another minute, and if nothing comes in, then we'll close it out for today. Again, the LBR Easy is a great robot for rapid prototyping at a low cost, where you're still required sensitivity of a system. With the graphical side, it makes it kind of easy to just do pick and place type of application, but the external API really helps with complex motion planning, or doing kind of like the good research that you might need for labs, things like that. So the other question was, do you need any licensing to use the software? All the licensing is handled by KUKA. So if you're using anything related to KUKA, all you do is you would purchase a system through us, and you would get all licensing required to use the external control API or the iKUKA graphical environment, things like that. So hopefully that answers your question. All right, well, thanks everybody. Have a great rest of your day, and feel free to send us questions if you have any later on. Bye.
Industrial intelligence.